Thanks. So I want to talk about some paper with Iordan, Ganev, and David Jordan about what happens to this 4G theory that Sam talked about and David talked about at root of unity. And let me be a little bit more precise what I mean by that. So David mentioned the skein algebras. So let's say sigma is a closed surface. David mentioned the skein algebras. So this is some associative algebras which depend on the parameter q. Okay, and so what happens is that there's something interesting happens at the root of unity, which is the following. So first of all, let's say q is 1. When q is 1, the skein algebra is just functions from the classical character variety. And if I literally mean skein algebra, is probably G is SL2. And what happens at nice roots of unity is that this algebra obtains a center, which is exactly the classical skein algebra. So in other words, this quantum skein algebra at some root of unity Q is a sheaf of algebras over the classical character variety. And then there is the conjecture, something called the unicity conjecture. Of 101. Is that if you look at this algebra over its center, it's generically Azumaya. Okay, so when I say generically Azumaya, this means that generically it's a vector bundle. Over the classical character variety. And each fiber is a matrix algebra. Okay, and again, this was formulated just for SL2. So this conjecture was proven 2 years ago. By Froman, Kania Bartoshinska, and Lei. But the methods are not very explicit. For instance, so it's generic Azumaya, but we don't know exactly where it's Azumaya, and it's completely unclear how to generalize it to other groups. So in my talk, I want to explain the following things. So first of all, I want to explain how to generalize the whole story for other groups. Second, the computation of the center is done by hands in the SL2 case, and it's impossible to do for other groups. So I want to explain why the center of the skein algebra at the root of unity is the classical skein algebra. And finally, I want to explicitly describe this Azumaya locus. Okay. Yep.
Generic vector bundle.
So
you use word generic two times. Generic vector bundle, and then you say about generic fibers.
geometric fibers. Yeah, this is geometric, sorry. Okay. Yeah, so let me first talk a little bit about the classical geometry of character variety. So I will explain exactly how it looks like and where this Azumaya locus will be. And then I'll talk about the quantization and how this 4D theory behaves at the root of unity. Okay, so a little bit about character variety. Okay, so recall that it was defined. So David mentioned this is, by this I mean the affine variety, which is defined by looking at the representation variety of the fundamental group, and then I take the affine GIT quotient by the group G. Okay, so a few things about this representation variety. So let me call the theorem. If the group is GLN or SLN, this representation variety is irreducible. Another thing is that there's a nice locus inside of this representation variety, which is called the locus of good representations. And it's the following. So this is an open subset.
You made a lowercase g, but that's not intentional.
Oh, sorry. Yeah. Yeah, so what I mean by good representations, I'll say the representation is good if, first of all, it's G orbit, so there's a G action by conjugation on these representations, is closed. And then you can also look the stabilizer of the G action on this representation. And it's the minimal possible. This is the center of the group.
Doesn't the second property imply the first?
Um,
I would expect so.
In the SLN, yes. I'm not sure about general. Okay. So so you have the good locus inside of the representation variety, and you can look at this image inside of the character variety. And here are a few things about this good locus. So this is a smooth affine variety. And this quotient map from a representation variety to the good locus is a G bundle. Okay, so it's as nice.
G1Z.
Yes, thanks. Yeah, so it's as nice as it can be. Okay, so this is about just basic geometry. Next, I want to talk about Poisson structures. So David already mentioned that there's a natural Poisson structure. On the character variety, so this is due to Atiyah Bott in the differential geometric setting. More algebraic setting is due to Goldman and a lot of other people. And this Poisson structure restricts to a symplectic structure on the locus of good representations. So this locus of good representations is exactly going to be my Azumaya locus that I'll explain. Yeah. Okay, let me say a few more words about this Poisson structure. So here I'm mostly talking about closed surfaces. So for instance, this result is about closed surfaces. So let's say you have some closed surface sigma, and it's written as a disk glued onto some open surface. And let me call this open surface sigma naught. And this is just a disk. Okay, then the fundamental group of sigma naught is a free group. So you can write local systems on sigma in the following way. So there's going to be some moment map. I'll explain what this is. Mod G. So here a moment map, it goes from the representation variety for this open surface, which is just G to the twice the genus, to the group, and it's just a product of commutators. And then you take the preimage of 1 of the unit, and then you take the affine quotient by G. So I'll just write this as G to the 2G. So this looks like Hamiltonian reduction, so I'll write this G to the 2G Hamiltonian reduction by G. So this doesn't just look like Hamiltonian reduction. It is Hamiltonian reduction, but in a certain group valid setting. So you have a moment map valid in the group rather than in the Lie algebra. But there's a well-developed theory of group valid moment maps. And so G to the 2G has a natural Poisson structure yeah, so this goes back to Semenov-Tanchansky and Falcon-Rossley. And then the Poisson structure you get on the character variety is just the one you obtain from Poisson reduction. Okay.
Is it a direct product, or are there some cross relations between functions under different factors?
It's a product of there are cross relations, but you should think about this as being g squared. So it's g squared times g squared. So in each g squared there's some complicated Poisson structure, and then each of them is a G Hamiltonian space, and then you take their fusion. And so there are some cross relations because you take the fusion. All right, so next I think I want to talk about quantization. So let me begin by just explaining what I mean by representations of the quantum group at a root of unity, and what exactly I mean by that for DTFT, for a root of unity. Okay, so let's say G is some connected reductive group. Plus some extra data that will be implicit. Then you can talk about the representations of the quantum group. So this is going to be a category. So this will be some vector spaces equipped with extra structure. These are vector spaces equipped with a grading. By the weight lattice of the group. And the operators of the quantum group. So by this I mean you have these EI operators, upper n, Fi upper n, for each simple root I, and n is a natural number. And you should think about this as divided powers. So you can think about this as being EI to the n modulo divided by the q factorial. And the same for Fi. And they satisfy standard relations like the Serre relation and the commutator between simple roots. Okay. So this has a natural braid-Mandelbrot structure. Maybe even let me say ribbon structure. Okay. So this is the category that the 4D TFT attaches to the point. Now let me remind you the category that attaches to the circle. So this is braid monoidal. To the circle you attach a monoidal category of quantum Harshad bimodules, which was modules over some algebra in RepQG. So this was the reflection equation algebra. An important point about this reflection equation algebra is that it has a certain isomorphism. So for every representation V, there is an isomorphism between OQG tensor V and V tensor OQG. This isomorphism is not just the braiding in general, but so I'm not going to explain what it is exactly. Okay, so using this formalism, I can now define, so I want to define quantizations of these character varieties, and the character varieties were obtained by Hamiltonian reduction. So I want to explain what is the quantum Hamiltonian reduction in this context. So to talk about quantum Hamiltonian reduction, I need to talk about quantum moment maps. Okay, so let me just define those. So let's say A is some algebra in RepQG. So quantum moment map is going to be a map from OQG into the algebra. So it's an algebra map. From the reflection equation algebra into A, which satisfies the following. Let's say such that the following diagram computes. So basically you can look at the left OQG action on A and the right OQG action on A, and you want them to be the same. So diagrammatically it means the following. So you can put OQG on the right using this tau isomorphism. So you can you have this diagram which expresses the left action of OQG on A and the right action of OQG on A, and I want them to compute using this tau isomorphism. So let me maybe just remark that you can replace RepQG by RepG, OQG by UG, and you can recover the usual notional quantum bound maps. Okay. So the usual quantum moment maps go from UG into your algebra, and they're J covariant.
Pavel?
Yep.
In David's talk, he listed 4 ways of quantizing character varieties and didn't mention this quantum Hamiltonian reduction. Is that because it implicit in this factorization?
Yeah, I'll get to that. I haven't quantized the character varieties yet. Yeah. So this is going to be a theorem that yeah, it can be obtained by quantization. So first of all, okay, so you have a quantum moment map. You can do quantum Hamiltonian reduction, which means the following. So I'll just write it's a quantum Hamiltonian reduction by UQG. So by definition, this is like in the usual setting. You divide A by some moment map ideal. I'll just write this as a relative tensor product, and then take UQG invariance. And then using the quantum moment map equation, you can see that this is actually natural in algebra. Okay, so where the quantum moment maps arise and how they're related to quantum character varieties. Okay, so suppose that, okay, so here's the theorem of Benzui, Brochet, and Iordan. So it has two parts. So first of all, let me assume that I have some module category over this category quantum Hertz-bounded bimodules. And it has some distinguished object. Okay, so you have an action of quantum Hertz-bounded bimodules. In particular, this gives you an action of RepQG. So this is a module category of RepQG. In particular, you can take internal endomorphisms of this distinguished object over RepQG. So this is going to be some algebra in RepQG. Then the claim is that this carries a quantum moment map.
That was stated incorrectly in our paper and proved correctly in our paper.
Yeah, okay. So, right. Also, there's a converse that if this this is a generator of M, so M is modulus over this algebra, then this is actually all you need to get the structure of modules over quantum Hertz-bounded bimodules. And second, how this is related to quantum character varieties. So recall that the category attached to the surface can be written as a relative tensor product of the category attached to the open surface, tensor RepQG, which is the category attached to the disk, over the category attached to the circle. So I can write this as a relative tensor product. And then endomorphisms of the distinguished object in this closed category. So this is the Skane algebra, is given by quantum Hamiltonian reduction. So this is, let me just write A UQG, where A is endomorphisms of distinguished object in this category. Okay. So in particular, yeah, you can write the Skane algebra at subroot unity as a quantum Hamiltonian reduction of this explicit algebra A.
Wait, sorry, the first equality there was the theorem of Cook. The first equality at the bottom of the theorem, the very bottom. The first equality on the left, yeah, that was the theorem of Cook that updated it?
Yes. Or if you like, that's what I want to define. That's going to be my definition.
Okay.
Yeah, one has to be careful. Juliet's theorem is for Q generic.
Okay.
So this is the claim that I made.
Yeah.
That it generalizes.
Okay. Yeah, and so the upshot is that these scaling algebras can be written as quantizations of the open character varieties, of open frame character varieties, which are just functions on g to the 2g, Hamiltonian reduction by UQG. Okay, so far this works for any Q. Q doesn't have to be a root of unity. It can be generic.
Sorry, I missed it. Did you define a distinguished object, or did you just say that it exists?
In part 1 or part 2?
Part 2.
In part 2,
Part 1, I thought it was just any
yes.
object. So.
In part 2, factorization homology gives you all. So these categories are canonically pointed. There's also a distinguished object. On the classical level, this is just the structure sheaf. Okay. Yeah. So as I said, this is so far a discussion that works for any Q. Now let me concentrate on Q being a root of unity.
So you talk the scaling algebra is defined to be the endomorphisms of the distinguished object.
Yes. Yeah.
In the case of the not reunion, it's not going to coincide with its original thing.
Well, the expectation is that it does, but the theorem is not there.
Yeah.
Isn't that what you said was super false?
No, I claimed that. Sorry, I said that the categories are not equivalent, and I also claimed that these algebras are isomorphic. They're the full subcategory where things match, and that's where I think.
Okay. So now let me concentrate on a case where Q is a root of unity. You have to put some assumptions on Q. I will not say precisely what it is. Q has to play nicely with G. Okay, so if Q is a root of unity, there is something extremely special that happens for the category representations of the quantum group. So let me recall that if C is a braid monoidal category, its Muger center is just the full subcategory in objects in C, whose double braiding is trivial. Okay, so you look at objects whose double braiding is trivial. In particular, this Muger center is not just braid monoidal, it's symmetric monoidal by definition.
You mean such that this is true for any y? Okay,
Yeah.
I wrote that.
So this is very similar to saying that you have an associative algebra, and you look at elements which commute with this element. So this is a higher version of a center. Okay. Yeah, so in particular, the Muger center of C is symmetric monoidal.
Is it related to the Dunefeld center at all?
No, this is a lower version of a center. So if you have a monoidal category, you can talk about Dunefeld center. If you have a braid monoidal category, you have a Muger center. So the Dunefeld center will be braid monoidal. This is higher, which is symmetric monoidal. Okay, and here's what happens at a root of unity. The Muger center, and again, I'm assuming that the root of unity is nice, is actually equivalent to representations of the classical group. So you can ask what happens if the derivative unity is not nice. If the derivative unity is not nice, what happens? Either there's some kind of language duality that happens here, so you don't get representations of the group, but you get representations of the language dual group. There might be something funny happening with the weight lattice, or sometimes you get representations of a supergroup if you have even a derivative unity.
Is there an a priori reason to see that rep G is acting, or is that easy?
Say it again?
Is there an easy way to see that rep G is acting on the rep QG there?
Sort of. Yeah. So this is yeah. This is exactly. So the action of rep G on rep QG is given by Lucius-Frobenius map. So the idea is that here we have some weight lattice. Here the weight lattice is scaled by L, by the order of derivative unity. And these generators E and F, in some sense you take their roots and they'll give you the actions in the classical group.
But the fact that it is exactly an isomorphism, it is due to mathematics.
Okay, so I don't know the history of this. The paper I learned it from is Chris Negron's paper, which is extremely recent. But it might be older for depending on which derivative unity you're looking at.
Nice enough mean large enough unity, or?
No, by nice enough derivative unity I mean it's odd derivative unity.
Oh, I see.
If the group contains a factor of type G2, then it's not divisible by 3, and things like that. Then it's not doesn't divide the determinant of the Cartan matrix, and so on. Okay. Yes. So this is the first thing to say. So the way you can think about this geometrically is the following. So you can think of saying that you have a family of braid-monoidal categories over BG, or it's a sheaf of braid-monoidal categories over the classifying stack. And if you have a sheaf for braid-monoidal categories over something, it's natural to ask what are its fibers. So you can ask what is its fiber over the base point. So there's a theorem over Hipov and Gates-Gorey. That if you look at the fiber of this sheaf of braid-monoidal categories, it's very explicit. This is given by representations of what's known as the small quant group. So this is called small quant group. Yeah, so this is the, if you know what the Lucius-Frobenius map is, it's the kernel of this. This equivalence.
Yeah.
No, I would rather say Negron's result implies that this is factorizable. So this small corner group is a finite dimensional half algebra. So it's a finite dimensional half algebra. Which is factorizable, which is going to be important. So let me just draw some imprecise picture of what's going on at the root of unity. So schematically speaking, you can say that this 4D TFT at the root of unity is a family of 4D TFTs parameterized by the same TFT where the root of unity is 1. So here we have repQG, which fibers over BG. So here we have a 4D TFT, which fibers over the classical TFT. And the difference is not, the difference between the quantum and the classical is not big. It's given by something factorizable. So it's given by an invertible for the TFT. The one associated to the small quantum group. And this is an informal explanation why we're getting Azumaya algebras on the surface. But let me get there. Okay. So, all right.
What does invertible mean?
Invertible means that, so this is a 4D TFT. Let's look at maybe 3 manifolds. So first of all, it's fully dualizable, so it's defined on everything. On 4 manifolds, all numbers are non-zero. On 3 manifolds, all vector spaces are lines. And on 2 manifolds, all categories are invertible in the appropriate sense. Okay. Right. Okay, so what's the story now? So the upshot, if you just compute this on the surface, what you get is this quantum scaling algebra is an associative algebra, and it contains a central subalgebra, which is functions on a classical character variety. But the classical character variety is a Poisson variety, so this is a Poisson algebra. So it's a central Poisson algebra. Okay, and then you can ask, okay, so you have an algebra and a central Poisson subalgebra. You can ask what kind of compatibility you can expect between the Poisson bracket on the center and the associative algebra structure on the whole algebra. And this is what's known as a Poisson order. So it's an associative algebra central subalgebra Z in A such that A is finally generated as a Z module. And in addition, you have an extension of the Poisson bracket to the whole algebra, by which I mean and a linear map So Z acts on itself by the Poisson bracket. You extend this to the whole algebra, which preserves Z and gives the Poisson bracket on Z.
Don't you also want this to be a homomorphism of Lie algebras?
You might require it to be a homomorphism of Lie algebras. I don't. Okay, so let me explain the source of Poisson orders and why they're useful. So the source of Poisson orders is the following theorem, which goes back to Hayashi and Brown-Gordon, who introduced the notion of Poisson order. And it's the following. So suppose you have AQ, it's also called AT, is a flat family of associative algebras and the inside of AQ is a central subalgebra. At some specific value of t, of the parameter. You have to assume that find a generation of AQ over Z, but this will be implicit. Then there exists a map from Z to derivations, and if D preserves the central subalgebra, this is a Poisson order. Okay. If you take Z as the whole center, then this automatically preserves. You have to be a bit careful. This is not unique. This map exists, but it's not unique. And you can change it by inner derivations. And I think this will spoil the map. Okay.
If it is the whole center, I think it is canonical, isn't it?
No. We can talk about this afterwards. Okay, so this is the source of Poisson orders. And why they're useful, it's the following result of Brown and Gordon. So suppose that A and Z is a Poisson order. And let's say you have a symplectic cleave inside of Z. Let me call this Z naught. So the spec Z is an open symplectic cleave. Then the claim is that A over this open symplectic cleave is actually a vector bundle, and any two fibers are isomorphic. Isomorphic as algebras. So the proof is in an analytic topology. The statement is it doesn't talk about topology.
Is it important that this is an open symplectic leaf?
Yes, there's a. Well, it's going to be. There's a flat connection along the only along the leaf.
But I think it's not, it may not be true if you take any symplectic leaf because you need the symplectic leaf is algebraic. You need some properties of varieties.
No, but he says the square per se is isomorphic. He doesn't say that they're locally at a point.
Do you know that one?
No, analytic.
No.
No, apparently the saying that there is connection. There's flat connection.
So D gives you the connection. I mean, it's maybe it's not flat. Let's say let's just say it's a connection, and using this connection, you can do parallel transport. This is a fairly short paper. If you want, you can take a look. Okay, so the upshot is that to prove that something is Azumaya, over the corresponding open symplectic leaf, it's enough to prove it generically. And then this machinery automatically extends the Azumaya property over the whole simplex leaf. Okay, so I'm not quite done yet. The problem is that this proposition doesn't directly apply in our case. So the problem is that we don't know that the skein algebras are flat. That first of all, that they're flat. So that's one thing we don't know. And the second thing over Q. And the second thing we don't know is what is precisely the center, so that it's not easy to check this condition. Okay, and the idea is that instead of doing something after the Hamiltonian reduction, I'm going to do something before the Hamiltonian reduction. And I'm going to do Poisson reduction of the Poisson order structure. Thanks. Okay, and so the goal will be to prove that actually this is a Poisson order and then prove some result about Poisson reduction of Poisson orders. Okay, so I don't have a lot of time left. Let me just kind of go schematically and explain the main tools and steps that we use. Okay, so it's easy to prove that before the reduction you have a Poisson order. Okay, so before the reduction, let's try to prove this actually as Azumaya. So I need to know what is the open symplectic leaf inside of G to the 2G, and I need to know that at one point it's a matrix algebra. So the second result is that we prove some general fact about symplectic leaves of Poisson G varieties. So the open symplectic leaf is given by the preimage of the big cell So here the big cell is the product of lower triangular and upper triangular matrices. Okay, so now we have a description of open symplectic leaf. So now it's enough to check Azumaya property at some point in the open symplectic leaf. And a natural point to do this is just the trivial element in G to the 2G. Yeah, at the base point. So at the base point, the category you get, this ZQ is basically a factorization homology over the surface for representations of the small quantum group. And as I said, this is factorizable, so this implies formally this is invertible. This is an invertible category, and you can conclude that the corresponding fiber of the scaling algebra is a matrix algebra. All right. So far, I know something before the reduction that I have generically an Azumaya algebra, and I know exactly what is the Azumaya locus. It's the preimage of the big cell. Okay, so now let's do the reduction. Well, so the idea is that okay, I like writing this Hamiltonian reduction. So you can decompose this in this Hamiltonian reduction in stages. And maybe let me mention that this idea to do Hamiltonian reduction in stages and many other parts are due to some people in the audience. Bezirkani, Finkelberg, Ginsburg. And Varniol Vasaro. So they used a similar technique, at least at this stage. Okay, and what I mean by to do in stages is that you can first take this quantum algebra, restrict it to the classical moment map ideal. Here you do Hamiltonian reduction with respect to the small quantum group. And then you take invariance, G invariance. Okay. So there are just a few more steps left. Okay, so next we proved that this Poisson order structure actually descends. So what this means is that the quantum character variety is a Poisson order of the classical character variety. So to prove that it's Azumaya, again, it's enough to do it generically. Upstairs, we know exactly the Azumaya locus. So what you need to do is to understand what happens with respect to after you do this small quantum group Hamiltonian reduction. And another fact we prove is that Hamiltonian reduction of an Azumaya algebra, or its a lemma, is generically Azumaya. Okay, so you get that this Hamiltonian reduction is actually generically Azumaya over the classical character variety. So the conclusion is that this quantum skein algebra, or the quantum character variety, is going to be is Azumaya over an explicit locus, which is the locus of good representations. Let me mention that for G being SLN, this is exactly the smooth locus. So this is as best as you can get. Okay, and I'm going to stop here. Thanks.